In this video, we're going to go through the process of conducting a hypothesis test for the mean when sigma is unknown. This is really similar to the section that we just covered where we did a hypothesis test for the mean with sigma known. The difference is going to be that instead of using a normal distribution, we will use a t-distribution in the exact same way that we did back in Chapter 8, going from a confidence interval for the mean with sigma unknown versus a confidence interval for the mean with sigma known. So it's the same distinction and pretty much the same types of requirements that we're looking at here. So I'm going to just jump straight in. It's going to have some of all those same requirements, those same conditions that we had back in Chapter 8. I'm going to just jump into the procedure. So the conditions for this to work, again, same as in Chapter 8. We need a simple random sample. We've got to have a sufficiently large sample size, so n has to be greater than 30, so on and so forth. All those same requirements from previous. Okay, so here's our procedure. Step 1, as in all hypothesis tests, we've got to state the null and the alternate hypothesis. State the null, and there's our table. Don't need that right now. State the null and alternate hypothesis. Okay, so our null hypothesis will take the form that mu is equal to some value mu0, and the alternate hypothesis will take one of three possible forms. It will either be that mu is less than some value mu0, that mu is greater than some value mu0, or that mu is simply not equal to some value mu0. And these three cases are respectively our left, right, and two-tailed versions. In the second step, this is where we define what we're going to consider weird. And depending on which approach we're taking, remember there's two approaches. We've got the critical value method and the p-value method. If we're doing the p-value method, this is super straightforward. So if we're doing the p-value method, all we need to do is basically find the significance level. So this is typically given in the problem. So give the significance level alpha. If we're doing the critical value method, then we need to actually find the critical value. So in the previous video, the critical value was either z sub alpha or negative z sub alpha or plus or minus z sub alpha over 2, depending on whether we were right-tailed, left-tailed, or two-tailed in our form of our alternate hypothesis. This is going to be the same thing, but again, remember, with sigma unknown, we're going to be using S instead. So we're going to be using the standard deviation of the sample rather than the standard deviation of the population. And this means we'll no longer be following a normal distribution, but instead we'll be following a t-distribution. So I need to replace all of these. These shouldn't be z's anymore. All of these need to be t's. So the critical value will be either t sub alpha, negative t sub alpha, or plus or minus t sub alpha over 2. Again, depending on whether we are right, left, or two-tailed. The one other thing that this critical value will depend on is our degrees of freedom. So remember, there's a lot of different t-distributions, and the one that we use depends on how large our sample size is. So we need to find the critical value for the given value of alpha and the given degrees of freedom. So degrees of freedom, which you'll recall is equal to n minus 1, one less than whatever our sample size is. So that's what we'll be doing for that. In the third step, we actually look at our evidence and see where it falls. So in the third step, we compute the test statistic. So compute the test statistic. And the test statistic is going to be the one thing that's different in all of these different hypothesis tests that we're going to do. So after we finish this section, we're going to do hypothesis tests for a population proportion, and then in Chapter 11 we'll be dealing with even more hypothesis tests, and this is really the main step where the procedure differs. All of them are going to follow the same 6-step procedure that I'm going to outline here. The main difference comes with deciding whether or not we're going to use a normal distribution or a t-distribution. So this will change a little bit, and the other main change will come with what our test statistic looks like. So in this one, the test statistic, again, it's not going to be a z-score anymore, it's going to be a t-score because we're dealing with a t-distribution. And it's going to be the following: x bar minus mu naught divided by our standard deviation, which is in this case s over the square root of n. So it's always going to be these same 3 components. This will always be our value of interest, so basically our evidence. Maybe that's even a better word to put there. Let me write it that way. This is going to be our evidence. It's the information associated with our evidence. This value here, make this a little more reasonably sized. This value over here, the mu sub 0, that's going to be the one associated with the null hypothesis. So it's always going to be the value from the null hypothesis. And this big thing down in the denominator is always going to be the standard error. So it's always going to be made up of these 3 components, our test statistic. It will be the value of interest from our evidence. We'll subtract off the value associated with the null hypothesis, and then divide by the standard error, which is, again, the standard deviation of our sampling distribution that we're using in this case. So that's our formula for the test statistic for this problem. The fourth step is going to differ depending, again, whether we're doing the p-value method or the critical value method. If we're doing the critical value method, if I can write today, so if we're doing the critical value method, we can skip this step. We get to skip step 4 because we already have all the information we need to compare. In the critical value method, you'll recall we compare either to z-scores or in this case 2 t-scores. I already have the 2 t-scores that we're going to compare. I have the test statistic. This is the one associated with our evidence. And I'm going to compare it to the critical value that we found back in step 2, which is going to be either t sub alpha, negative t sub alpha, or plus or minus t sub alpha over 2. Again, depending on whether we are left-tailed, right-tailed, or two-tailed. So I have my 2 t-scores to compare. And we're ready to go if we're doing the critical value method. If we're doing the p-value method, instead of comparing to z-scores or t-scores, I need to compare to areas or probabilities. And so we have the first probability over here, this alpha, our significance level. That's the probability that we consider weird, right? That's where we defined weird. And the p-value is going to be the other area, the area associated with the test statistic. So we need to compute or find the p-value. Which is, again, the area to the extreme of the test statistic. Okay. At that point, whether I'm doing the critical value method or the p-value method, I have everything I need to compare. And so step number 5 is where we decide whether or not our results, our evidence, is weird. So determine if our result, by which I mean the evidence, is weird. And we'll use this to decide whether or not we're going to reject the null hypothesis or not. So the criteria that I look at in this case, there's two different. So if we're doing the critical value method, I need to compare those two t-scores. So our result is weird if the test statistic, which is t, is more extreme, so further into the tail, be that the left tail or the right tail, whichever side we happen to be on, is more extreme than the critical value, which is, again, either going to be t sub alpha, negative t sub alpha, or plus or minus t sub alpha over 2, depending on the form of our alternate hypothesis. So there's what that one looks like, and if we're doing the p-value method, don't know why it always zooms out to that. Maybe I will remove that table in the future. You know what? I'm going to remove it now. Let's delete this. I don't want that to keep doing that. We'll put it back in later. Okay. Yeesh. Okay, so p-value method. Again, we're trying to determine if our result is weird. In the p-value method, our result is weird if our probability, which is the p-value, so our result is weird or unlikely if the p-value is less than the significance level, which was alpha. Basically, the significance level alpha is what we define to be weird. Maybe we said we're going to consider something weird if it occurs less than 5% of the time. If our p-value winds up being smaller than that number, if it winds up being like 2%, 0.02, we would consider the probability of our outcome, which is what the p-value is. The p-value is the probability of getting the evidence that we got. We'd consider it weird because it's less than 5%. So if this number is 2% and this number is 5%, then our p-value is a lower probability than the cutoff for what we were going to consider weird. And we will say that, yes, our result is weird. And lastly, step 6, we need to draw our conclusion in plain English. So state, and I should do this. Let me sneak in one other thing for step 5. If our result is weird, if it is weird, we reject the null hypothesis. Because it's only weird under the assumption that the null hypothesis is true. We run through the entire problem assuming the null hypothesis is true, and at the end, if we're getting weird results, we say maybe it was a bad assumption to assume the null hypothesis was true. And so at the very end, we need to state our conclusion. Again, in plain English, there should be no jargon in this, no special statistics terminology, something that your son or daughter or kid sister could understand, somebody with no knowledge of statistics. So that's the idea. So looking at this all in one spot, this is our 6-step procedure, and it is pretty much the same 6-step procedure that we've been doing for the hypothesis tests back in the previous section in 9.2. So let's do an example of this and see how this works. So here's my example. Let me zoom in a little bit. Okay. So in this example, let's say the following. So a phone company like a mobile carrier, Verizon, T-Mobile, Sprint, something like that, they claim that their network drops fewer than 5 calls a year on average. So per customer, not total. 5 calls per year per customer. A random sample of, let's say, 52 of their customers shows that they actually had an average of 5.8 dropped calls. 5.8 dropped calls with a standard deviation of, let's say, 2.3 dropped calls. So, they've made a claim that they drop fewer than 5 calls per year. Our evidence seems to indicate that they drop more than 5 calls per year. Is this strong enough evidence to basically refute their claim, to say, no, we think you're lying, your network drops more than 5 calls per year? Or could this just have been an artifact of sort of just noise? Just by dumb luck, the sample that we took just happened to have more dropped calls than their average customer. So that's kind of the question. Can we conclude that their claim is false? And we're going to do it at a significance level of 0.05. So there's our question. Okay, so we're going to go through this problem again. Just for practice, I'm going to do both the p-value method and the critical value method, but again, both methods are not required. In some of the future videos, I'll just pick one or the other. but I just want to do this one so again we can get practice doing both approaches. So step number 1, we need to state the null and alternate hypothesis. And so they look like the following. Here's our null hypothesis, here is our alternate hypothesis, and before we even start, I know that this is going to be mu equals, and this is going to be mu something, I don't know if it's greater than or less than, and whatever number I put right there needs to be the same number that goes right there. So that is what I know from the beginning. So I need to figure out what number goes here. The null hypothesis, looking at this, so let's think about this. They're claiming that they drop fewer than 5 calls a year, but our evidence shows that they drop more than 5 calls per year because it showed that they drop 5.8 calls per year. The number that goes here has to do with the claim that they make. So it's going to be the 5. This is going to be the number 5 in both of those places. So even though they claim to drop fewer than 5 calls per year, we're going to put mu equals 5. 5 is sort of the right at the cusp of their claim being true to their claim being false. So if they dropped exactly 5 calls per year, which is the high end of what they said they do, we will say that that's sort of the transition from anything less than this number, their claim is true, anything bigger than this number, their claim is false. So this is the cutoff, but again, this always has to be an equal sign. Even though their claim is that they drop fewer than 5 calls per year, I don't put a less than symbol here. This always is an equal sign. We always put in the number that is the cutoff between their claim being true and their claim being false. The alternate hypothesis, what the evidence seems to show is that the average number of dropped calls is larger than 5. So that's my alternate hypothesis. I really think that the evidence shows that mu is actually greater than 5. They drop more than 5 calls per year. So that is the idea. But again, let me circle these in red instead. Those two numbers should be the same number. Easy things to remember. It needs to be the same number in both places. This always has to be an equal sign. So there's our null and alternate hypothesis. This alternate hypothesis turns out to be right-tailed because it's mu greater than some given value. So we're going to wind up doing our calculations in the right tail. So step 1 is done. Step number 2, we're going to define weird. And I'm going to draw in a picture as part of this that we can come back and reference. So we're going to do this in 2 different ways. We're going to define it based on the critical value approach. Let's just abbreviate that way, and also with the p-value approach. The p-value one is the one that's easy in this case. The p-value method, we just need to know what alpha is, and it was given in the problem. We said alpha, our significance level, was going to be 0.05. So there's the number right there. That's what we need to put right there. The critical value, this is where we need to determine whether we're dealing with a normal distribution or a t-distribution. And so this is going to be the trickiest part. I phrased this question up here in such a way that I didn't use any symbols. On the homework, you'll notice they'll often use symbols. They will put sigma equals 5.8, or they'll do an s equals 5.8, they will do x bar equals 5.8 over here, and they'll do either sigma or s equals this 2.3 down here. They will use the symbol to indicate whether this standard deviation, that's 2.3, whether it is a population standard deviation or a sample standard deviation. I have not stated anywhere in the problem explicitly what this is, but we need to be able to, again, interpret what the wording of the question says. It says that a random sample of 52 customers showed an average of 5.8 dropped calls with a standard deviation of 2.3 dropped calls. In that sentence, it means that this 2.3 dropped calls, this standard deviation, refers only to this sample of 52 customers. It's not 2.3 dropped calls from all the phone company's customers. it's 2.3 for the standard deviation just of these 52 customers. That means this is a sample standard deviation, and we're using S. So this is the idea. Based on the fact that we're dealing with the sample of 52 customers, and this is the standard deviation of 2.3 dropped calls, this thing must be a sample standard deviation. So it must be S, not sigma. And because it's dealing with S, this implies that we're going to be using a t-distribution. If it had been sigma instead, we would use a normal distribution, and this would be a problem just like the ones from section 9.2. But because this is a sample standard deviation right here, that's what is the indication that we're dealing with S, and that means that we're going to be doing a t-distribution. S and t always go together. So coming back down here, I know that this is going to be t sub alpha. I know it's going to be t from the discussion that we just had that we're dealing with a t-distribution, and I know it's going to be t sub alpha because we've got a right-tailed hypothesis. T sub alpha is the one that goes with right-tailed cases. All I need to do to figure out this number is recognize that we've got alpha equals 0.05, and we've got our degrees of freedom, which is going to be 52, which is our sample size, minus 1, which is 51. So our degrees of freedom is 51. Now I want to use that table that I took away. Let me insert it here real quickly. Got a PDF. I want this one. And there's the one I need. Okay. So here's that table. Let me move it over to the side, but somewhere where we can still take a look at this. Okay. So here's the table that I'm going to use to determine the critical value t sub alpha. When we're trying to find this, I need to figure out the degrees of freedom. Our degrees of freedom is 51. So I just need to go down to the row labeled 51. Oh, there is no row labeled 51, so what do we do instead? We have to round again in the conservative direction. So we want to use a sample size in this case for our degrees of freedom that is the more conservative. So that means I'm going to use 50. We will assume that we had a smaller sample size than what we actually had. So this is the row that I'm going to use. What is the area in the right tail? It is going to be this area of 0.05. And I will find where those two numbers meet. And we get that number sitting right there, 1.676. So this number is going to be 1.676. And again, let me draw our picture so we can follow this. It's going to be a picture very similar to the one that we have on this table here. So let me move back over to here and zoom in. We found our critical value. Whoa. Good enough. So here's the picture that we're dealing with, and I want you to get practice drawing this picture. Here's my distribution. It's the distribution of all the possible x bar values. And it looks something like this. We are assuming that our average value sitting right here in the center of this curve, this is the one that is our null hypothesis. We're assuming that this is mu equals 5. That's literally what we assumed in our null hypothesis, is that the average of our sampling distribution curve is at 5. And we're interested in figuring out where that 5.8 is going to fall. We know it's above average, so it's somewhere over here on the right. But I want to decide if 5.8 falls over here, that's not such a weird result. But if it falls way over here, that's a really weird result. And so we are defining what we're going to consider weird. And in this case, we're saying, okay, I'm going to cut off, if I can write this here. Come on. There's my cutoff. The area of this region is alpha equals 0.05. This is the region that I'm considering weird. Anything over here is weird. Anything over here is not weird. So this is my weird region. This is the part of the tail that I'm going to consider weird, and it has an area of 0.05. So it's the most extreme 5% of the area under the curve to the right. We've defined, in the p-value method, we defined this weird region by its area right here. This is the significance level. If we're doing the critical value method, I define the weird region by this t-score, 1.676, and that is the t-score that tells me where the boundary of this is. So here is t sub alpha equals 1.676. That is the region that I'm considering weird. And now we just need to decide where our result falls. Is that 5.8 going to be over in this region where it's not weird, or is it going to be over somewhere in this region where it is considered weird? That is going to be the question that we look at. So let's take a look. Step number 3, we need to compute the test statistic. And again, the formula for the test statistic, it's a t-score. We look at the actual evidence, we subtract off the presumed value from the null hypothesis, and then we divide by the standard error. And so for us, x bar, the value of interest, is 5.8. That's the average number of dropped calls we saw in our sample. The presumed number is only 5 because that's how many they made in their claim. So in our null hypothesis, we're assuming they really only make 5 dropped calls. How weird would it be to get 5.8 dropped calls if the true average is really only 5? And now we put in our standard error in the bottom. This was the 2.3. That was the standard deviation of the sample. And we divide by the square root of our sample size, which is 52. And when I plug these into the calculator, if you're doing it in the calculator, you might want to toss parentheses around these things to make sure we don't make any mistakes. I got 2.508-ish. Good enough, at least. So 2.508. That is my test statistic. So now we just need to get our things for comparison. Right now I have my test statistic, I have the critical value. I could compare these two numbers if I was doing the critical value method, and we would see, yes, sure enough, it looks like this result's going to be somewhere over here in the tail. It's going to be in the weird region. But if I'm doing the p-value method, that's what we need to take care of in step 4. So if we're doing the critical value method here, we get to skip this step. We've already found the two scores, in this case t-scores, that we are going to compare, but if we're going to do the p-value method, I'm not comparing t-scores, I need to compare two areas. We already have one area, it's that alpha equals 0.05, it's the area of this region on our curve over here, and now I need to find the area associated with this value. So we need to find the p-value, which is again the area associated with this t-score of 2.508. And to do this, we're only going to be able to ballpark the value if we're using the table, so using table A3. So let's go use table A3 to try to approximate this value. In a little bit we'll do this whole thing on the calculator and we'll be able to find the number more precisely on the calculator. So let's come back over here. So for this problem, again, row 50 is the only relevant row for this problem. All these other rows have to do with different degrees of freedom. We haven't changed our degrees of freedom. It's still 51. We're still using row 50. We're stuck in this row. I want to find an area associated with this particular number. And if I go through this list of all these t-scores, so in this list, these numbers in the middle, these are the t-scores, and these numbers up here are the areas. It's not quite as detailed of a list as table A2 was. So if I go through this, obviously the number 2.508 is not showing up anywhere in this list in row 50. So the best I'm going to be able to do is ballpark this. If I can figure out roughly where 2.508 falls, which it looks like it's going to be between these two results, I'll know that the area associated with it must be between the areas associated with these two numbers. So if 2.508 is in here, the area associated with that t-score of 2.508 must be between the areas associated with 2.403 and the area associated with t equals 2.678. And those two areas going up are going to be 0.01 and 0.005. So that's how we're going to do this. I know that my t-score, so RT, which is 2.508, is between two other t-scores. It's between, let's see, 2.403 and 2.678. So again, our number falls right between these two numbers right here. And so those are the two numbers that I'm now using for this problem. That's where I got this number and this number. Oops. So that tells me that the p-value, which is the area associated with our 2.508, must be between the two areas associated with these two numbers. And so if I go back to the table, we mentioned them a minute ago, the area associated with the 2.403, tracing up to the top, is 0.01. So this number over here is 0.01. And the number associated with the 2.678, let me just zoom out so we can see all of this at once. There we go. The one associated with the 2.678 is this number right here, 0.005. So this number is 0.005. So I don't know the exact value of our p-value, but I know it's between those two numbers. This one is the larger number, so these symbols actually switch directions. So I don't know the exact value of the p-value, but I know it's between 0.005 and 0.01. So I have a good sense of roughly how small it is. And so now we can, step number 5, determine whether or not our result is weird. So let me zoom back in now that we have these values. So, is our result weird? The answer is yes. And it's yes because, coming back to our picture, we found that our t-score, our result, wound up falling somewhere over maybe there-ish. There is t equals 2.508. And this little tiny area in here, that little area, which I'll do down here because there's more room, that's the p-value. And we just found that the p-value, I don't know exactly what it is, but I know that it's less than 0.01. That's what we found down here with this number. The p-value is less than 0.01. So I don't know that exact area, but I know it's less than 0.01. And that's enough to tell me that our result definitely fell into the weird region. So it's weird because if we're doing the critical value method, our t-score, t equals 2.508, is more extreme. Our test statistic, 2.508, is more extreme than the critical value, which was t sub alpha, which was, I think, 1.676 was the number that we had. Let me just peek. Yes, 1.676. For the p-value method, we know our result is weird because the p-value itself is less than 0.01, which is definitely less than 0.05, which is what the value of alpha was. So whenever the p-value is less than alpha, our result is weird, and that's exactly what we see in this case. Our result is indeed weird. Okay. All right, come on. So step number 6. Last thing with step number 5, sorry. Let me just delete this again so it stops trying to zoom out to that. Let me delete all of this as well. Okay. Hopefully it'll stop zooming out to that. Okay. So back to this. Is our result weird? Yes, it's weird because we found that our test statistic 2.508 was more extreme than the cutoff for weird, which was the critical value, t equals 1.676. Or alternately, doing the p-value method, we found that our p-value is less than 0.01, which is definitely less than 0.05, which was our cutoff for weird. That was the value of alpha. So because our result is weird, this means we are going to reject the null hypothesis. Our result is only weird assuming that this is where the center of the curve is. If this is the center of the curve and our result's way over here to the right, it's a weird result. But if the center of the curve was actually way over here, if this was what our curve looked like, instead, well, now this result right here is kind of close to the middle. It's not that weird of a result. And so that's what we're going to see in this particular case. So what does this mean in plain English? Looking at, again, our result is weird under the assumption that the center of our curve is at 5. But if the center of our curve is somewhere over here to the right, then maybe our result isn't so weird after all. Maybe it's close to that center of the curve. But if the center of our curve is to the right, that means that the center of the curve, mu, is greater than 5. It must be a larger number. And that's exactly what the alternate hypothesis stated. So we've rejected the null hypothesis that mu is equal to 5. And we're going to accept the alternate hypothesis. We think that mu is greater than 5. So if we think that mu is greater than 5, the average number of dropped calls from this company is greater than 5, what does that mean about their claim? Their claim is false. So the evidence suggests, and strongly suggests, that they drop more than 5 calls. And so that is our plain English conclusion in this case. Their claim is false. The evidence strongly suggests that they drop more than 5 calls per year. This isn't the only phrasing that you could use. You'll notice on the homework they'll use a very consistent phrasing that's sort of a drop down where it says the evidence is or is not strong enough to reject the null hypothesis. In plain English, there's many ways to phrase it, but this is the idea. At the end of the day, their claim is false. They drop more than 5 calls per year.